Welcome to Embedded. I'm Elecia White, here with Christopher White. This week, our guest describes himself as a nuclear engineer, carver of Fortran and Python, somewhat ex-sysadmin and Perl coder, law tech wrangler, and invertebrate science geek, which is different than inveterate science geek. He promises never to program websites ever again. Our guest is Bob Apthorpe.
Howdy.
Now, before we get really started in talking to you, I do have to mention that Hackaday is having another SuperCon. Remember, I did a show last year where I talked to all the organizers and had a good time. It's going to be in Pasadena this year, November. Oh, it's going to be in Los Angeles this year. Southern California, you know, they're all the same. November 4th through 6th. And I was going to tell you the call for proposals is open, but I think it closes September 1st. So if you're not listening to this right away, it's over. But you can still go. It'll be cool.
Hi, Bob. Thanks for being here today.
Hey, thanks for having me.
So I gave you a little bit of an introduction, but maybe you can tell us more about yourself.
So I had kind of a odd career path. Got a bachelor's and master's in nuclear engineering, which basically means I know how to boil water and shuffle paper and scare people at cocktail parties. I'm not sure people actually have cocktail parties anymore, but if they do, I'm okay at scaring people. Not intentionally, just by virtue of being there. Maybe that's why I don't get any invitations anymore. Anyway, that's beside the point, really. But after graduation, I went down to Louisiana and worked at a power plant for a while, and I realized I was not cut out for the power plant and Louisiana lifestyle, and I moved to Texas and turned into a web programmer and sysadmin during the dot-com boom and bust. And then I found myself back in the nuclear industry where I am kind of working at what was my dream job back in 1990, doing severe accident work and environmental remediation type of stuff. Basically, and anything that can explode with hydrogen that isn't a Zeppelin, I'm probably involved with.
What is the thing you wear to determine if you've had too many
Rads?
Oh, the
dosimeter?
The dosimeter, old school, some people will call them a film badge back when they used to have like photographic film in them. It's, let's see how the technology goes on that. It was like a piece of photographic film because that's how they discovered radioactivity in the first place. And then it went to something like a calcium fluoride or something chip, which would soak up radiation, and then you could heat it up and it would give off light later. So you could kind of see how much radiation people picked up. But I'm not sure what they're using now, if they're still using that, or if, there's a lot of the tiny little ones that, like the tiny Geiger counters that, are wearable. There's also some really interesting silicon or semiconductor counters out there as well.
You've managed to derail your own show in 6 seconds.
Sorry.
No, not you. I meant her.
He's over here mouthing to me, like, why did you ask? And my question was really going to be, do you wear a dosimeter often?
Me?
Yeah.
Me? No. I work in an office. I pilot a desk. They don't let me near the interesting stuff.
Well, then I would think cocktail parties wouldn't be as big a deal. It's the people who are actively glowing that you don't want to invite.
So those people are outdoors on the back porch with the fire dancers, and they're part of the show. Those people are invited. It's the kind of the people who spend their time in the eerie glow of the computer and don't really have social conversation. Those are the ones it's like they're less scared of your glow and more scared of your brain.
It's a different kind of glow.
Exactly.
Okay. I know you listen to the show sometimes, so you are familiar with lightning round, and I'm not even going to explain.
Good.
Fire away.
Favorite subatomic particle?
Neutron, because it changes things.
Science, technology, engineering, or math?
Oh, man. Blindsided already. I'm going to go with math.
Beach or mountains?
Mountains.
Favorite isotope?
Ooh, that's Probably deuterium. D. Heavy hydrogen.
Favorite fictional robot?
Gort.
Worst version control system you've ever used?
None.
Well,
second to
none.
Second to none would probably be okay. I would say SCCS, except I'm going to go with RCS because I didn't know it was RCS when I accidentally used it. Because of a unfortunate human factors problem, the C and the V keys are right next to each other on the keyboard. So if you go to type VI to edit something and you accidentally type in CI instead, your source file disappears and is replaced with something.
I think I've done that. I think I remember that too.
And you're like,
Yeah.
What did you do? Where did my file go? And then you're like, what? But no. And then the irony of it is it's put it into version control where it's supposed to be safe.
No, I'm sure I did this.
Yes, I do recall this.
I'm next. Favorite invertebrate?
Favorite invertebrate? Ooh. You know what? I like the Monterey Bay Aquarium with the jellyfish exhibit. I love the jellyfish.
And they expanded the jellyfish exhibit to be a tentacles exhibit, and now they have all sorts of cephalopods as well. So
nice.
Cuttlefish and octopi, and it's just fantastic.
I also like the Sardine Tornado because you just go in that room and then you just start like spinning a little bit, and then it's like, whoa. And then, it's like Sardine's Revenge.
So, yeah, the Monterey Bay Aquarium as a whole is pretty good. But you don't have a particular favorite variety? Stubby squid, I have to say I like, just octopus in general, because I stopped eating octopus once I found out they played with toys. I could not ethically eat an animal that got attached to a Mr. Potato Head. There's a new book called The Soul of the Octopus out, and I'm totally looking forward to it, because the last time I read about octopi intelligence, it was fantastic.
Yeah, you have to keep them engaged, or they get bored and they get cranky.
Sounds like Christopher.
That sounds like me.
What science fiction technology or concept do you think will be real in our lifetimes?
Yeah, at this point, I'm going to have to say the 1950s era rockets that just go up and then come back down and land. I mean, I know that's not nearly as cool as the Singularity or
Not sure the Singularity is cool.
I'm not sure shooting the Falcon rocket is fair because it exists.
I mean, well, yeah, but that's true. I mean, that is cheating. Okay, so that's cheating.
Well, I haven't done it with people in it, so that's fair.
But I don't know. I mean, we've already done pretty much every kind of dystopia. With the possible exception of gray goo. And, I think that's only because nobody looked in my refrigerator when I moved out of my last apartment.
Well, and CRISPR's a thing, so gray goo's coming.
Okay, yeah.
All right. Last question, which I did not write. How far away from a nuclear reactor should I live to be safe in the event of a disaster?
Well, if it's provided it's not human error, if it's bad enough to break the reactor, you kind of want to be inland and uphill. There's
away from the prevailing winds.
Yeah, pretty much away from the prevailing winds. I mean, but you'll probably have a couple of days to sort out what you're going to do if we note that anything's going south. The last reactors that tended to, blow up without warning were kind of like the Russian RBMKs, the Chernobyl-style reactors, light water reactors, which are the ones that are out, the ones that are in primary use today, take hours or days to get to a point where, they're really sad. I mean, you look at Fukushima, and that took days to evolve. The issue is you may want to just stay at home and keep your windows closed and then like avoid the roads, because the roads will be more dangerous to you than the radiation will.
All right. So advice given, but what does a nuclear engineer do? Or more specifically, what do you do?
What do I do? There's, to kind of look at the general thing, nuclear engineering is it's one of those late model engineering degrees, and it turned out to be sort of a jack of all trades. The background, my background has been a lot of thermodynamics and heat transfer, a little bit of chemical engineering, a lot of physics, a lot of math, and then a small amount of just the nuclear physics of like, well, how do we turn this into that, and like how does shielding work, and how do you build something critical? How do you keep it critical? How do you make it not critical? But my day-to-day job, I work on accident analysis and waste technology and software development. So it's a really interesting. My position is pretty interesting because you never know what you're going to be facing from week to week. A lot of the specific stuff I work on is hydrogen control, and hydrogen shows up, from a lot of different sources, either from, like in the case of a severe reactor accident where you have steam and zirconium cladding reacting to form zirconium oxide and hydrogen and heat. You have to get, now you have explosive gas and extra energy, and your fuel has all fallen apart. But there are other conditions where, say, you have radiation in water. You wouldn't think that water is that complex, but once you start actually looking at what, all the chemical reactions of water coming apart and coming back together again, you put some radiation into that and you're going to knock hydrogen loose. So you may have like a pool full of spent fuel, or let's say an ion exchange column that does like water cleanup, and you've pulled all this radioactive material out of the water, and now it's stuck in these resin beds it's a big filter. So you've pulled all this radioactive stuff out of the water into the filter. That's great, but now it's in the filter and it's still irradiating the water, and is that going to make hydrogen gas, and where is that going to go? And hydrogen, as we've seen with like people trying to have like hydrogen powered vehicles, hydrogen is a pain in the rear to deal with, because it's a sneaky little molecule. It squeezes out of places.
It's tiny. I believe it's the smallest one.
It is. Yes, it's so tiny, and it just sneaks past things. It diffuses through things. It causes like metal embrittlement. It's irritating.
It's the perfect fuel.
Exactly. It's a perfect fuel. It'll, because you can fill up your car with it and then wait 24 hours, and then your gas cap is like embrittled, and then all your hydrogen is leaked out, and then you have to buy more. It's awesome. And it's not a greenhouse gas. So, it's the second most, common element in the universe outside of stupidity. So,
so you're not in the pocket of big hydrogen.
No,
not yet.
I am I'm in the pocket of small hydrogen. It's like, okay, so how do we deal with it when it gets out? So, it'll show up from, either chemical reactions or radiation or, all sorts of things. So that's one of the kind of generic issues that shows up in like, waste and severe accident type of stuff. So,
but you talk a lot on your Twitter account, which is how I know you.
Yes.
About software.
Yes.
How does that come into this?
Okay, so, we're not allowed to touch anything anymore. So we have to do everything with modeling. There's a lot of stuff that we don't want to try and simulate. The nice place about, the nice thing about where I'm working now is we do a fair bit of experimentation, but we also do a lot of basic, math and engineering work, but we also do software development. So we would like to know, say, for example, when when your reactor runs out of water, how long is it going to take to fall apart? What's going to happen when, will this melt? If it does melt, how much melts? If it keeps melting, is it going to stay at high pressure and then, squirt molten fuel all over the floor? Or is the bottom just going to fall out like a wet grocery bag and drop all this stuff onto the floor? And then, it's going to eat into the concrete and, all that. And that sounds really flippant and all that. But, because there's so much bizarre phenomena going on. But, that's one aspect. So I work on, software simulations of severe accidents, like Fukushima. I actually, I think it was the last year or two, I worked on on some chunks of code for predicting what the shape of the hole in the floor was going to look like as things ate into the concrete, and also what happened when you basically flush molten core debris down a drain. So, it's like
is that recommended?
I don't think that's recommended.
It's not.
It's not like baby turtles.
No. Well, you shouldn't do that either.
No, you really shouldn't.
No. But it's actually more. It's more like dumping grease down, like if you made a big pot of bratwurst and you have all this grease left over, and you just toss that down your sink trap. While it's hot and in the pipe, that's fine because it'll keep flowing. But
it doesn't stay hot for very long. It
doesn't stay hot for very long, and it starts to coat the inside of the pipe. So the question is, and this is where this is why we look into things like this. When you have this molten stuff flowing through a tube, it's going to start solidifying against the wall of the tube and making the tube smaller. And the question is, will the tube freeze shut before whatever molten goo you have upstream transfers to the downstream place? And the reason people were asking this question is not because they're really concerned about the pipe, but what they want to know is, since they can't just go into like the Fukushima reactors and see where the molten fuel debris went, they'd like to be able to predict, is it all underneath the reactor, or is it, down this sump, has some of it flowed through this sump piping over into a different part of the reactor, and they don't want to be surprised by it. They want to know what they're up against when they're cleaning this up before they actually go in. So that's kind of what we try to do. And that's one of the hard things about writing this kind of software, is that have been so few failures that there's not a lot of real world data. I mean, we're kind of a victim of our own success, and I'll be the first to, admit that I'm happy about not having real world data to work off of. But a lot of this is based on experimentation, and there's a lot of uncertainty into it, in this. So, you're never, I don't know, it's interesting, but, in some sense, it's kind of like video game physics. I mean, does it look kind of right? It's like, well, yeah. It's like, okay, well.
Until you actually go and look and find out whether or not you were right, all you can do is guess and hope. And smaller models and bigger models, yes. Yeah,
a lot of what we do is we'll take, known problems or known accidents, and we'll try to benchmark our code against that. So for the past maybe 2 years, we've been working with a lot of Fukushima data to try and benchmark the new models in our software against what they saw. And the problem with that is that, when you're dealing with kind of an incomplete data set, because that reactor was not set up as an experiment, and it was not operating with like all of its monitoring system. It was, it had, they were doing everything they could to keep the thing together. So taking data was not their primary concern. It's like this is. This isn't like, I don't know, what is it? Is it an Independence Day or something? It's like, let's talk to the aliens. It's like, they're actively trying to kill us. Just kill them. It's like, no, we have to understand them. It's like, no, hit him with a shovel. We'll do the science later.
Well, and that's always the problem, is that if you do get your simulation to do what was seen, now when you run the simulation again, it works, but you may not be sure that it will work next time because there were variables you didn't get to see.
And you're dealing with such low probability events, and the closer you simulate the actual conditions, the more uncomfortable everybody gets with your testing, because now you're not just using like simulated materials. Like one of the projects I worked on was for the Hanford Defense Site in Washington State, and they've got an old spent fuel pool from the defense reactors out there, where it's a couple hundred yards from the Columbia River, and it's 50 years beyond its design life. So, they have to clean this pool out, and so they're doing a lot of testing. It's like, okay, can we, how do we move the sludge around and stuff? You can't do a perfect simulation, because if you're doing a perfect simulation, now you're actually using, radioactive materials, and nobody wants to do that. So you kind of, everything is going to be, you're going to be dealing with the approximations, based on the kind of modeling and the kind of experimentation that you can do. And it, comes back to like, how much are you actually going to have faith in the model, and how far are you going to push it? Like, are you, do you just want to see kind of a ballpark of where it's going to go, and then you're going to apply some sort of conservative design when it comes to actually working with material? Or, because you don't want to get in a point where you believe the model, garbage in, garbage out. You don't want to, treat the model as gospel. It's just a model.
Have you ever had a software bug that indicated the world was about to end? No, not close enough. It sounds like
no, but I mean But the weird thing is, when people have found serious, like, I won't say serious bugs in terms of giving thoroughly wrong answers in the code, but more of, like, say a module was coded wrong, and you compare it to the actual math or the engineering that the software design. You're like, okay, this doesn't implement the design correctly, or we've put the a completely wrong constant in here, and you realize that it doesn't matter. It's like you've gone through all this effort to model a phenomena, and at the end of the day, you run your simulation, it doesn't make any difference, because
that wasn't what was driving.
It wasn't a critical, parameter.
When you talked about your schooling and training, you didn't mention software engineering or computer science or software development. Do you have formal training in that?
Sort of. So I took this weird career arc. It's like you sit down in your first day of orientation. They ask you what they ask you to pick a major. And at age 18, you're not really capable of making that decision intelligently. But I kind of flipped a coin. It's like, well, I was good at chemistry and good at computers, and I like both of them pretty equally. And but I'm going to go with chemistry because I don't want to be tied to a terminal for the rest of my life.
How's that working out for you?
Yeah, see, that's one of the things where I look back, it's like, this is possibly the dumbest thing I have ever said.
Well, to be fair to yourself, I mean, you couldn't have predicted that everyone would be tied to a terminal no matter what they do anymore.
Okay, fair
Not
enough.
The people who actually need the dosimeters.
But what ended up happening was that I did pretty much everything but get a computer science degree when I was in college. So I went the engineering route. I went from chemistry, and it's like, okay, I don't know what a chemist does long term, so I'll go into chemical engineering. And it's like, well, I don't know what chemical engineers do either, but this is getting really hard. My grade point is plummeting. I'll go over to nuclear because that looks interesting, and they'll let me. They'll take anyone. That is not a fair assessment.
I'm going to strike that.
But, yeah. Well, guess who's rejecting my donation? Nope. Keep your money, buddy. No. So it. But while I was pursuing the engineering side, I was also taking classes in machine language and architecture, and mathematics classes in combinatorics, and I just doing a lot of. I mean, not the formal computer science curriculum, but I always had kind of one foot in that space. And as my career has progressed, I went and did risk assessment at a power plant, and then in the mid '90s, it's like the way I phrase it is, I couldn't stand being at work and I couldn't stand being at home, so I moved to Texas and worked for a game company, and then I ended up in the .com universe. So, I stayed. It's like I basically kept doing the computer stuff that I had been doing all along, and kind of the engineering side turned into kind of put on a back burner, and I kept the understanding of reliability analysis and risk assessment, because that's completely applicable to system administration or software development. Maybe you're not hauling out your book on thermodynamics a lot, but you are looking at okay, well, what's a conservative design principle, and how do we predict where things are going to be soft and code defensively. But I ended up spending a lot of time looking into the history of computing and trying to backwork knowledge of databases and operating systems, networking, and then looking into kind of the more esoteric ends or more professional ends of software development. Things like literate programming, or what is this the right language I should be using for this project? What other tools do I have available to me? And then things like risk assessment comes into play when you start dealing with version control systems, because it's like, okay, well, how are we going to safeguard our code? So that becomes second nature to anybody who does software for a living. Maybe.
Well, it doesn't. It doesn't. I mean, I was just thinking as you were talking about programming for different industries, and that whole model of risk assessment, and doing formal risk mitigation analysis and that kind of thing. That only exists in a couple of places, and everywhere else, it's kind of either implicit, like, okay, well, we're going to use a version control system, and our IT people will be responsible for safeguarding our code. But there's not really any other attention paid to the kinds of risks that maybe could be mitigated if they were more explicit.
Well, I think if you come from that background, from the idea of mitigating risks and considering them, you apply that wherever you are.
Yeah, and that's the thing about it. And the interesting thing is that wasn't exactly part of the curriculum in school. I mean, there's only so much you can teach in the somewhere between 4 and 8 years you're in college. But a lot of it came from being just on the job in what they call a high performance organization. When you're just not allowed to have the same level of failures that are tolerated in other organizations. And especially when you've had high profile accidents, and then they've spent a lot of time and effort, looking at, how did this come about, and how do we prevent this from happening again, and not, trying to prevent just one sort of accident from happening again, but like looking at contributing factors, not just hardware, but things like, organization, or, a lot of human factors, things like, I worry about diverting into a long spiel on this one, but like the 3 Mile Island accident is a really interesting example, and I draw a parallel between 3 Mile Island and compiler warnings, which you would not necessarily put in the same sentence. One of the contributing factors to 3 Mile Island was they have these what are called annunciator panels. It's just a big array of lights. And when something happens in the plant, a light will come on. Now, that could be anything from like your tank is low and doesn't have enough water in it to your core is overheating and you need to shut down right now. So there's a sort of a wide range of potential, so the severity of conditions that will cause a light to come on. And there's hundreds of these lights along the top of the control panel. And one of the problems at 3 Mile Island was a lot of those lights were on, and they didn't mean they weren't necessarily critical, but they were always on. And the problem was identified that if you had an issue where something broke that really was important, one light would come on, and you would have to identify that out of the 100 or so other lights that are already on, which, if we go back to the notion of like compiler warnings, it's like, well, most of them don't matter. It's like, oh, you're casting from this, assigned to unsigned integer or something like that. And you're never going to use a negative value for there, so it doesn't matter any. But if you've got 500 compiler warnings and one of them is actually significant, how are you going to see it right in all of that? So there was a strong emphasis, of all the lessons learned after 3 Mile Island, there was a strong emphasis. It's like, look, if those lights aren't important, turn them off. Either come up with a justification why you don't need that light, or go fix the actual underlying problem that makes that light be on. And yeah, it's a pain in the butt, but that's the cost of doing business in that space. So if you're, same thing, if you're going to be a professional programmer, it's like turn off your compiler warnings. I mean, not turn them off.
Turn them all the way up.
Yeah, it's like you turn them on to pedantic, and then you address them piece by piece, and you make them go away the way an adult, responsible programmer would do. And that's hard to do when you're faced with schedule and budget issues and maybe a culture that doesn't respect that kind of, it's like, that's just pedantic BS. Why are we wasting our time with this? It's like, well, it's a practice of good engineering.
I do not understand how vendors let out code that has hundreds of warnings. I'm working on a project now for with the Freescale Kinetis line, and it pisses me off that they have so many warnings in the Freescale code. In their example code.
Yeah.
That, somewhere in there is probably an uninitialized variable, and it's going to take me weeks to find it because I have to deal with the other 500. And then when they release a new set, am I going to redo it, or am I just never going to update?
Yeah.
But it's funny you talk about this because it's a problem that's very prevalent in medical devices right now. That they set the medical devices to beep or warn pretty early, thinking, well, you wouldn't want it to get beyond that. That would be dangerous. And then we end up with all of these beeping warning devices that nobody can, the nurses can't pay attention to that many beeps.
And that's the worst part about that is that's a problem that was recognized as, as early as like the Vietnam War, where they had, all these, the beeping and blinking of the avionics systems. It's like, okay, well, let's alert, let's alert pilots if they're getting, probed by radar and if they see this and that. And so there would be so much noise in the cockpit that pilots would start turning off all the warnings because they couldn't think, because there was it's like the same problem with every monitoring system out there. We'll just enunciate to everybody, and and then you're so overwhelmed with signal. Well, that it all becomes noise.
Yeah.
I mean, it's all, this is all coming down to signal to noise ratio, and it's like once you get to that critical level of noise, you start turning everything off and just ignoring it, or you accept it as normal, and or
have systems which are intelligent enough to synthesize some of those individual warnings and say, this condition is severe, and then have it say to you, pay attention now, this is a severe condition, rather than, well, these 5 things are happening. So I don't know if you make sense of it or not, but here are the 5 things.
Well, there was I don't remember the name of the software, but I remember at the Lisa conference one year, they were talking about something that would go through the syslog, and it would convert syslog entries to essentially like a musical tone or a chirp. I don't remember the name of it. I'm sure this can show up in the show notes. I will take that on as an action item for later. But it would convert these to, just a noise, like a chirp or a beep or something, and then you would be able to listen to your syslog as if it was like a jungle.
Music. Yeah.
Yeah. So it's it's like you hear the normal chirping of birds, and then there's this squawk. You're like, that's not right. And that, it's like try to, use different senses to try to alert people to, significant events. Because, we don't have to do everything through, parsing text. I love text, but, when you're faced with a wall of text, maybe you need to find a different way of doing your pattern recognition.
But this problem of filtering out warnings and making sure we get errors, it seems like many industries have to rediscover this same really critical piece of design. How do we cross boundaries? How do we get this from avionics, which is how I first heard that nothing goes wrong unless the plane is about to fall out of the sky. Everything else is unimportant.
Okay. For me, I've kind of taken a 2-prong approach. In the last decade, or not decade, but the last 5 years, I've spent a lot of time looking at how other industries handle the same sort of issues. Looking at things like food safety, looking at aircraft. How do airlines or the FAA regulate their sort of systems the way because we people in the nuclear industry, we have the same sort of issues of we can't accept the same level of failure as having to reboot your coffee maker. In the same way that you can't have a satellite where somebody has to go and turn it off and turn it back on again, or an airplane, turn it back off and turn it on again. So you look at other high performance organizations and find out what kind of challenges they face, or even not super high tech ones like food safety. Like, how do you do surveillance to make sure that food's safe, and how do you do the monitoring on that? How do you handle epidemiology? Looking out. You have to intentionally look outside of your own industry, and it's really hard when you have like a normal life and whatever other job responsibilities you have. The other thing is to, if you have changed industries, like when I went from nuclear to like sysadmin, I didn't leave all of that safety and reliability thinking behind. So when I was in like high availability systems classes, I'd be in a workshop with some people and they're talking about single points of failure and mean time between failure. I'm looking at it, I'm like, that's 1940s or 1950s era reliability analysis thinking. That's ignoring so much of, interfacing systems and systemic effects, things like common cause failures. Like, you remember a couple of years ago when there was some company making capacitors and somebody else had stolen their electrolyte formula, but badly. So there were a number of counterfeit capacitors that went out on the market, and they started causing board failures all over the place. I don't know if you know.
Yeah, remember that.
If you remember that. I mean, I think I had a motherboard go out from that. The capacitors would, sausage right up and, you lose your board. But it's like, that's what's called a common cause failure. It's like, it's something that affects a bunch of, it's not endemic to the design. It's something that a number of components will have in common by virtue of the fact that they came from the same manufacturer, or they bought the same lot number of capacitor, from different manufacturers, things like that. And that's really kind of confounding when it comes to doing like quantitative risk assessment, when you're kind of like saying, okay, well, I've got diverse, redundant systems. I got one DNS server from one vendor and one from another vendor, and they're plugged into separate switches and they're in separate power supplies. And it's like, okay, yeah, but they all bought capacitors from this same bad vendor. So, it's the same issue that can take them all out. So it's like, even if you do go to the point of that, trying to design your system to be very resilient, you still have to worry about getting sandbagged by something like that.
And then, they have the problem that maybe they get a chemical lot and it goes to different manufacturers of capacitors. And so it's very hard to battle this all the way through.
Right. So really all you can do is do your best with trying to design some resilience into your system and presume your stuff is going to fail and be able to deal with it gracefully. That's easier said than done.
It often is, because the way that we deal with failure tends to be, oh my God, it failed.
And then there's somebody on the phone who's like, why isn't it back up? Why isn't it back up? And they calling every 3 minutes, and you're trying to solve the problem. And, eventually you just pick up the phone and say, yeah, we know there's a problem and we don't care. We're lying on the floor in a pool of bourbon.
Or after the problem, tons of corrective measures are made that focus on that one problem to the exclusion of a bunch of other things forever.
Right. And there's thinking that goes beyond, like, well, what went wrong, and let's do a root cause analysis, and let's, close all the barn doors for all the horses. It's like, well, have you ever considered that, like, we don't ever pay attention to what we get right, and how how the resiliency of, the human aspect of it. I mean, we always consider the variation of performance to be a bad thing, and we would like to replace everyone with robots so that, they all work perfectly. And it's like, well, but maybe what we want is to, instead of controlling that variability of performance, we want to like steer that in a direction where it's like, well, we want performance variability, but we want it to be good. So, I mean, this is kind of more philosophical stuff. There's a guy named, I think, Eric Holnagel, and he talks about safety 1 and safety 2. He's got a slim book where he talks about the distinction between kind of this old school and, a newer way of looking at this stuff. But it's, that's another thing. It's like, kind of looking into the safety literature and looking at, other accidents in other industries, train accidents or aircraft accidents, the process industries or chemical plants, looking at the history of space flight. It's all, it's hard to get outside of your comfort zone. And I know, especially for the field that I'm in, it's like, nobody talks to us and we don't talk to anybody else. So it's, it's really hard to cross-pollinate or get new information in or share it with other people. You really have to make a concerted effort to do that.
Well, that's often difficult because your industry is sort of known for being a little stagnant.
Oh yeah. Yeah. I told you about the issue of manufacturers of parts. The manufacturers go away, and the parts have lasted so long that there's no one to build replacement parts, and these plants are running a lot longer than anyone expected them to. And, a lot of it turns into a victim of your own success of, it's like, well, if you make something indestructible, you only need to make one of it.
Yeah, if you make a part that's supposed to last for 50 years, who's going to make the next one?
Right. It's like, well, it hasn't failed. Well, I guess we're out of business now. We've sold our 3.
Yeah, exactly. One of the things you've been mentioning is engineering and software design. And then there's this thing called programming, which to me is probably it's the skill. It's the typing, where the software design and the engineering are more the intellectual, artistic creation parts. But that's sort of me. What do you see as the difference?
This is an appropriate part where I'm taken to the woodshed over my comments about software and engineering. I think software is more of an art or a craft. There's a limit to what you can do from sort of the mathematical basis. And I think engineering has a lot of art to it as well, but there's a lot more physical forces you can rely on. There's just sort of a lot more axiomatic things you can rely on in, say, the traditional or harder engineering. Like, gravity is going to pull in a certain direction. I mean, unless you're in outer space. But I mean, by and large, you can rely on gravity. You can rely on things like pressure. You know that energy is going to go from hot to cold until everything's kind of lukewarm. There's all those things that you can depend on. I mean, you can't push a rope. Is always a good engineering adage. And with software being so abstract, I think it's really hard to do. It's really hard to, I think, treat software in sort of an engineering kind of way. And I think this is complicated when you're dealing with hardware, because then you're actually dealing with more concrete things. Like you can't split a pixel, despite certain people trying to tell graphic designers to do just that. You just can't do that.
Yet my brain is sitting here going, but you could dither, you could go back and forth. It's sort of like, and that's totally a software perspective on it.
I can explain sub-pixel rendering with anti-aliasing. Of course, you can do a quarter of a pixel. Yeah, sure.
And we can layer a bunch of abstractions on there. But when when push comes to shove, you're going to have to send an electrical signal down the line to the monitor to address that pixel, and you're going to have to tell it what its intensity is. And at some point there is rubber and a road and a point where they meet. Whereas it's like, well, let's just slather another layer of abstraction on there. It's like, well, I mean, Fortran had a really interesting bug. I mean, the language itself, not. Well, actually, I'm not sure if it was the language or specific implementations, but since everything was done by reference and not by value, you could, in some cases, inadvertently redefine constants, like numerical constants. So you could say, if your compiler was not particularly smart, you could say like 0 equals 1, and then from then on, 0 was equal to 1. And this would cause a great deal of consternation.
Seems fine.
Yeah.
Do that all the time.
Sure. That's it's a great thing about standards. It's like, well, we'll just redefine the standard to dark.
But engineering, and I know we've got some Canadian listeners that every time we say software engineering, they're like, no engineering, you can't use that word.
And believe me, as a longtime former resident of Texas, I mean, even me with an engineering degree could not call myself an engineer without having professional engineering licensure. I would need a PE license to legally call myself an engineer in Texas.
Which is a series of exams as well as some overseeing work experience.
It's the basic professional professional certification, like medicine or law, where you have some ongoing, you have a code of ethics, and you've got some commitment to continuing education. That's there. I don't know that there's a similar thing in the software industry other than just basic, career survival that you have to stay. And it's like you don't have an option of continuing software education. You're either, continually learning or, you're, I don't know,
about to be fired.
But yeah, exactly. So,
and there's no ethical oversight, no ethical training.
But you're already bound by, all right, I'm not going to get into this, but you're already bound. If you're working in a regulated industry, you're already bound by those regulations. So if you're working on a medical device, you already have to follow the FDA process. So ethics on top of that seems...
Well, I can see where that would be...
That's imposed ethics.
It's all imposed ethics.
Poor Bob.
Sorry, Bob.
You might think it would be superfluous, but there's things like, conflict of interest,
sure.
Or, just, in basic... there's some weird aspects of like trade in there. As someone who's, slowly studying for, PE licensure, I'm familiar with this. I think when I was a sysadmin, we had been pushing for some sysadmin kind of certification. And again, this was also with like code of ethics and continuing education type of stuff. But there is, in fact, I was really surprised to find this, that there is a PE exam section. Like you can go in for a PE license in software engineering. I'm still somewhat confused by this, but I sprung the $40 or $50 for the study guide for the software engineering PE exam, and it's kind of interesting. I think it's more focused on like requirements management and the whole like CMM capability maturity model kind of way of looking at things. But it's not really. That's more managerial and organizational than from a practitioner standpoint.
Well, and IEEE tried to have a software license or certificate, and it was pretty cool, except it was a lot more manager than practice. So, but I don't know that it went anywhere other than at them advertising to themselves.
Yeah, and I think that was sort of a problem when we tried to do that within the sysadmin community, because there wasn't an actual, I won't say there wasn't a need for it. It was just that there wasn't as strong of a need for it as we maybe would have liked. And even with like, normal, like, mechanical or electrical or chemical engineering, you can easily, spend your career without a PE license. You don't need one. It just, the times when you do need one, it's because you're working on something that is particularly critical to health and safety. Mm-hmm. Like like you're mentioning, like medical devices, or for example, like civil or structural engineering. That's primarily where you're going to see, you're going to see a lot of PEs in that. That area, just because you don't want buildings to fall down and crush people, or like in the case of nuclear engineering, looking at high pressure steam piping. All of that has to be done up to some pretty strict codes. So there's a lot of oversight on that, where you have to sign on, review and sign off on documentation to make sure that your steam system doesn't explode and kill a bunch of people. And and actually, if you look at the history of the development of high pressure steam, it's a every time you see these regulations, you start realizing that they're pretty much written in blood. Somebody had to die before before these safety regulations went into place. For railway or
FDA or automotive or aviation.
Yeah, exactly.
All these things. They didn't write them to be annoying.
Yeah, it's not somebody. It's not like somebody's in a committee just trying to make life miserable for people by saying make sure that the guy who routes your natural gas to your boiler is actually a competent engineer. I mean that the whole reason that natural gas even has a smell because that's added. Natural gas by itself is odorless. They added a smell to natural gas so people would know that there was a gas leak because of a pretty horrible accident in New London. Is it New London? Yeah, New London, Texas, in the 30s, where they took some gas from a oil field and piped it into a high school, and they ended up blowing up the high school and like 300 kids, and it's horrible. And and that's the whole reason you can't call yourself an engineer in the state of Texas without having a PE license. So, not to get all heavy and morbid on this, but there's you look at the history of this stuff and, you realize that you got to, there's a pretty heavy weight on your shoulders and you have to take this kind of stuff seriously. And you would hope that your management and that your coworkers would kind of go along with you on the ride. It's like, this is inconvenient and it maybe adds cost or delays schedule or something. But at the end of the day, you're doing the right thing. Yeah.
But it's got to be a team effort. It's really tough to have that from just above.
Absolutely.
And it is equally tough to get the training and to want to talk to people about it only to have everyone say, no, that would cost too much and not consider it. So it's really finding the right team and the right industry.
And also, it shouldn't necessarily be an either or. You're either in a regulated, safety conscious industry or you're not. I think there's a spectrum of, you don't necessarily have to spend a fortune on this or, go to tons and tons of classes, but be aware of the consequences of your decisions and be aware of the trade-offs you're making when you're maybe playing fast and loose with stuff. The same way we don't want the stereo in your car, has like maybe some USB update on it. It's like, well, what if that accidentally gets triggered and you're not in the middle of a USB update? It bricks your stereo, and then there's nowhere to, what does that say to your customers? Why is your system designed that way? Did you think this through? It's a minor economic loss, but it's an embarrassment to the company. It's really kind of avoidable. And it also, speaking from personal experience, it sucks if you're in the beginning of a road trip and your stereo just decides to brick because, the vendor didn't think through how it does. It's like, when are you going to do a USB update on your stereo? Why would it, why isn't there like a button that you press to just say, reset it to factory default conditions? I look at stuff like that, like, what are you thinking? It's like, well, they're not. It's like, okay.
They don't have to. Nobody told them they had to do more than what their job is today.
Yeah.
And, I hope listeners know that I never have believed that. Your job is what your job is, and you should be thinking about how it affects everybody. But let's go into something happier.
Let's
switch topics.
Yes.
You do stage improv.
Well, up until about 2008, I was performing on stage down in Austin, Texas. And then I moved to Chicago, the capital of improv in America. You can argue that, but, it's going to be a hard argument to make. And I stopped doing improv because I couldn't get downtown on a regular basis. But it was, I started doing it in 2000 and never really intended to go on stage. But that's just how things wound up. And it was really kind of a transformative experience for me. Speaking as kind of, the technical nerd introvert type of person, being able to kind of work through things that are kind of uncomfortable and, putting yourself out there socially and taking a lot of risks in a safe environment to the point where it's kind of second nature to take those risks because that there's really no consequence to failure. which is an interesting kind of like reversal on the whole, we're so worried about failure. It's like, well, on the other hand, it's like some failures are not worth worrying about. And in fact, some failures are actually good.
I can see how improv would give you that. I mean, if you start a skit and it all goes horribly wrong, half the time that's what the audience wanted.
Oh, yeah. I mean, there's some, but there were also people, friends of mine who just couldn't come to see a show, and I'm assuming it's not out of quality issues, but that they actually, it would make them very uneasy watching people take risks like that, because they feel so bad for this, like, oh, that's going so horribly, or I'm on the edge of my seat because it just makes me nervous because I don't know what's going to happen next, and neither do they. But a lot of it is just, the practice of working with other people and paying very close attention to other people and the give and take of control. And
the realization that being humiliated doesn't actually kill you, and it doesn't last that long.
No, and
especially just keep repeating it.
Yeah, exactly.
Well, there is the rule of threes. You do something funny once and it's funny. Do it a second time, it's funny but not as funny. Do it a third time, it's hilarious.
Yes, indeed.
And I think there are higher order resonances of that, because I think by the time you get to 9 or 27, it is excruciatingly hilarious. I've watched some people from LA do that, and it's just like, you're not going to keep doing that, are you? Yes, you've totally committed to it, and you're just like, they're not. No, they are, and it's pretty. Maybe it's kind of a. It's not so much of an inside joke. It might be. I don't know that too many people would be. So let's watch how long they're going to do this, but they played it off really, really well.
Everyone who made it all the way through the cat episode understands exactly what you're saying.
But so it's. It helped me a lot deal with failure and to take risks and put myself out there, socially, to not worry about silence. Listen for pacing. How much are you talking? How many people are in this room? 3? Okay. Then you should probably be talking about a third of the time. And you need to kind of like be listening for that. If you find yourself continuing to talk, it's like maybe you need to stop for a moment or check in with other people. So
how has it affected your job? Do you make more jokes to get people to do what you want, or is it just easier to introduce yourself to people?
It's a lot easier to introduce myself. You watch to kind of see. It's like, is anyone talking to that person? Well, go over and introduce yourself to that person. See if just pay attention to like the kind of the atmosphere. Pay attention to other people. And it's not so much all about me. It's about kind of us. Find out what needs to happen and do that. But also, a lot of us don't be afraid to speak up or take risks. And that, and that's where there's sort of an issue with, some stuff is great in an improv class where there's no consequences to failure. Well, in real life, there are consequences to failure, and there are consequences to speaking up. So you have to make a judgment of whether, you can't just go into life like it's, an improv class, because that's going to get real ugly real fast.
Yeah.
But the other thing is, one of the great things that I got from the whole process was this notion of status, of the king and the peasant, who's in charge, who's got the status, and the games that people play. Friends will regularly undercut each other and mess with each other. And this, if you watch who has the high upper hand or who has got the higher status, that will shift very rapidly up and down, back and forth between people who are equals. They are not completely level, but it will, you'll watch one person rib one person and the other person will, accept that, and they'll just give as good as they get. Whereas you end up with other lopsided, arrangements, the boss and employee type of, situations. But once you you can play some really interesting games with that. Like, well, what happens when the king is taking orders from the servant? And that kind of like role reversal, and there's comedic effect to that, but there's also practical effects to that as well, because one of the techniques people use to kind of puff themselves up is to push other people down. And if you don't realize that's a common technique, and you're not used to like paying attention to this sort of thing, you may be victimized by the situation where somebody's like, it's like, oh, our code's delayed, but it's not as delayed over, it's as delayed as Team B's, which is, got all these other problems. It's like, and then now you're in a reaction role. If you're on Team B, it's like, wait, why is this guy, saying bad things about us and making us look bad? And now I'm angry and upset, and and I'm trying to react to that, and I'm reacting emotionally. Whereas, if I understand that, Team A is behind and this guy is trying to save face by making us look bad, it's like, okay, I see what you're doing, and I'm not going to react, I'm going to choose my reaction. So there's a certain amount of self-control, and, it takes a lot of the emotional sting out of it, especially once you know what's going on. And these are common tactics that people use. And I mean, this is not meant to be, manipulative. I mean, it's just understanding a lot of, basic social things that I'll speak for myself, that, the introverted, technical nerd, it's like, well, if I was that gregarious to start out with, I might not be doing this job, but I'm more comfortable with the machines and the math. I'm more comfortable with that than, the interpersonal stuff. And once I kind of understand the interpersonal stuff and how it works, it takes all of its power away. And then I can kind of, stand my own ground and choose my own reaction. And it doesn't mean that I'm necessarily overly assertive or overly aggressive. There are times where it's like, well, maybe I'll just, let somebody do that. It's like, okay, well, it's not worth fighting over, but I'm not going to get upset about it. And I get to choose my own reaction. And that just leads to a lot less stress on me. I'm in control of me if I'm not necessarily in control of the situation. I at least understand the situation. So that kind of stuff is I think, super helpful. I mean, not necessarily just my environment, but I think just any workplace environment.
So, sounds like stage improv can give you a leg up if you are not a political animal and want to know what's going on in your organization. Also, it could be helpful for new managers trying to figure out all of these weird cues people are getting that they are not happening right.
Yeah.
Because so many managers are engineers who are promoted, except if you don't get the training, it is pretty bewildering as to these people all want things from me. How do I help them, and how do I say no? And if you don't know how to do both and delegate too, I don't know. It sounds like stage improv could be really helpful.
Oh, it's it's easy to say it's kind of a panacea and cure all for things. I mean, it can be great therapy. It can help with a lot of just being able to play through things and be a total jackass to somebody else, like just a mean-spirited bastard to other people. When that's like totally counter to your own personality. And then the other half of it of like when somebody's making life bad for you that you intentionally go out of your way to make things worse. How could I make the situation worse for me? It's like, okay, well, it's also raining, I mean, things like that. And just like real, being able to, kind of manipulate that and put yourself through that in a, kind of a safe venue where there aren't any consequences to failure, playing through that stuff. I mean, when do you get to play like that?
That does sound like fun. You're making it sound like a lot of fun.
Well, again, I'm not getting commission, but your mileage may vary, but I got a lot out of it, and I was very, I'm very happy with it. I'm still, even though I'm not actively performing, I highly recommend it.
You're
just
not actively performing on stage. You may actively be performing in a day-to-day way.
Yeah. The thing is, most of your day isn't scripted anyways. So, you improvise every day, so you might as well get good at it.
Cool. Well, I think we are about out of time, and I wonder if you have any thoughts you'd like to leave us with.
Yeah, it's actually a good dovetail with the improv part, because it's like, cut yourself some slack and don't be afraid to fail. Find yourself some opportunities to, push yourself to beyond where you're comfortable, and, let things fall apart, and then smile about it, accept that it broke, and move on and get used to that, because the only way you're going to learn, learning happens through failure, and it's an active process. And I know, at least from my electronics hardware projects and early in life, of them either starting on fire, getting kicked to death. Now that I can accept failure, it's a lot easier for me to do, things that I wish I could have when I was, 20 years younger. The electronics doesn't work. It's like, okay, well, it's on fire. Okay, well, time for a new eval board.
Sometimes it is best to be a duck, to have the water just go right off. Yeah, before I get all metaphorical and stuff, you have a giveaway, just not for your company, just because you want to give away some things.
No, I love the show, and I like the audience, or I love the audience and I like the show. Some combination of like and love of audience and show. And I like these books. So I am giving away 3 books that I very much enjoy. And I will let you figure out who they go to.
Well, I want to talk about the books, but before we do that, I would like you, Bob, to think of a number, and Christopher to think of a number, and me to think of a number. Don't tell me the number.
What is this bounded in any way?
Actually, that's what I'm going to say next is do you want to bound your number?
No.
All right, me neither.
Okay.
Bob, unless you want to bound your number, we're not even going to bound them. They could be anything.
No, we're not programming in Ada here.
Okay, so you listeners, send us a number, any number, one of the numbers that exists.
There's a few.
There's a few, and send it to us by October 1st, and you will win a book. And I guess the book that I will be giving out will be, Atomic Accidents, whoever gets my number. Bob tells me it's written by someone who really knows the technology and history and does a fantastic job explaining complex failures in an engaging way without resorting to fear-mongering and hyperbole. It's a book about the subject that Bob would have written if only this person, Mahaffrey, had not done first. Chris, you're going to give out the second book, whoever gets your number. And that's Safeware by Nancy Leveson. I'm doing a really good job with the names. Maybe you should read that one.
Leveson.
Safeware. Let's see. It is, even though it's 20 years old, it is full of amazing insights for delivering safe, reliable systems and ways of looking at the organizational context in which these systems are built and used. Even if you aren't building safety critical systems, it's a fantastic resource and thought-provoking.
be really sad if Christopher chooses his own number. And Bob, the one that I have left to you for your number.
I am giving away. Well, I'm giving
You're
away
giving
all
all
of them.
of
But the one I am presenting is Every Anxious Wave by Modavio. It is the only fiction book on the list, involving indie rock and punk rock and time travel, and love and loss and redemption and finding things you didn't know you were looking for. And we only have a couple more days this summer, so get your last bit of summer fiction reading in. And full disclosure, it is written by my lovely and talented ex-wife. So I'm super, super proud of her, and the book gets really good reviews, and I'm in there somewhere. Maybe not directly, but I know I'm in there.
That sounds like fun. I'm tempted to go get all of these myself. Our guest has been Bob Apthorpe, Senior Nuclear Engineer. Thank you so much for being with us.
Oh, thank you for having me. I love it.
Thank you also to Alan for suggesting Bob and even reminding us both. He also suggested some questions, so we really appreciate it. Hope you got most of them answered. Although we skipped a large section, so maybe someday we'll have to have you back to talk about testing and standards and whatnot. Thank you also to Christopher for producing and co-hosting, and of course, thank you for listening. You know we have a blog, embedded.fm/blog. Did you know that Andre has started a new series about STM F something Discovery 1 boards, the F4 Cortex MF4. This is really going badly. I should have planned ahead on this part. But it is a good series. It is far more organized than I am today. And Chris Feck will be returning with his MSP430 series as soon as he gets done, I don't know, vacationing or some nonsense. We also have a YouTube channel for these podcasts, so you can stare at our wonderful logo while you listen to the audio at 2x speed. I don't know. Somebody wants it. People are listening. I don't know. The contact link on Embedded FM will direct you to the YouTube channel. It will let you email us, or it will let you sign up for the newsletter, which has been marked as spam for the last 2 weeks, but is finally fixed and should go up on, I don't know, Tuesday or something. Now, a final thought. Let's go with Mark Linus from The God Species, a book about Chernobyl's disaster. At 1:24 a.m. on 26 April 1986, Chernobyl's Unit 4 reactor exploded after staff disabled safety systems and performed an ill-advised experiment to check, ironically enough, the reactor's safety. Embedded FM is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive any revenue from them. At this time, our sole sponsor remains Logical Elegance.